Welcome to lecture number 7. This week we're going to start talking about chapter 14, double and triple integrals. We'll talk about double and integrated integrals over rectangles, double integrals over general regions, and then area by double integration. And then finally, to get ready for the next lesson, we'll go back to chapter 10 and we'll talk about polar coordinates. First, double integrals over rectangles. But before that, let me remind you about Riemann sums from Mathematics 1. If we wanted to define a definite integral over the closed interval from A to B, our strategy was that we partitioned our interval into lots of smaller intervals, and they didn't have to all be the same width. And then on each one of these small subintervals, we draw a rectangle, and such that the height of the rectangle approximates the function. We add together all of the areas of the rectangles using negative area if the function is a negative at that point. And then we add them up to get a Riemann sum. If we take the limit as the number of rectangles increases, that's the same as saying the limit as the norm of the partition tends to 0, then we get our definite integral. We're going to be doing the same idea for double integrals. Let's suppose we have a function of 2 variables, and let's suppose that the domain of our function, or at least the region that we want to integrate over, is a rectangle. The rectangle where x is between a and b and y is between c and d. We need to partition this rectangle into smaller rectangles using some vertical lines and some horizontal lines. And as before, these rectangles don't all need to be the same size. The area of the kth rectangle we're going to call capital delta capital A subscript k. And that will be the width of the rectangle multiplied by the height of the rectangle. And then on each one of these small rectangles, we're going to be drawing a cuboid or a column such that the height of the cuboid approximates the function. And then we're going to add together the volumes of these cuboids, something like this. This will give us our Riemann sum. If we take the limit of the Riemann sums as the number of rectangles tends to infinity, or to say it another way, the limit as the size of the partition goes to 0, then we get our definite integral. The double integral of f over the region R is the limit of these Riemann sums. So same ideas as you were doing in Mathematics 1. For example, calculate the volume under the plane z is equal to 4 minus x minus y over the rectangle R, which is the rectangle where x is between 0 and 2, y is between 0 and 1. In other words, we want to calculate the volume of this three-dimensional object, which is shown in the picture here. Now, we know that x goes between 0 and 2, so we're going to be integrating between x is 0 and x is equal to 2. And to pair with that, we're going to put a dx on the end. And we're going to be integrating between y is 0 and y is 1, because in our rectangle, y goes between 0 and 1. And paired together with these, we're going to put a dy on the end. So we're doing the integral from x is 0 to x is 2 of the integral of from y is equal to 0 to y is equal to 1 of 4 minus x minus y dy dx. This is an integral inside an integral. And that's how we're going to calculate it. First, we're going to calculate the green integral, and then after we know that, we'll calculate the integral with dx in. Just as when we were doing partial derivatives, when we calculated the partial derivative, we pretended one of our variables was a constant, we just differentiated the other one. We're going to be using the same idea here. When we do the green integral, we're integrating with respect to y. We've got an integral which ends in dy. So we're going to pretend that x is a constant. The integral of 4 with respect to y is just 4y. The integral of x, pretending that x is a constant, with respect to y is just xy. And the integral of y is y squared over 2. When we replace y by 0 and 1, we just get 7 over 2 minus x. Now we have another easy integral to do. The integral of 7 over 2 minus x with respect to x. So of course that's just 7 over 2x minus x squared over 2, calculated at 0 and at 2. That gives us the answer 5. The volume of the object in the picture is 5. Now let me remark, in the previous example I was writing x equal to and y equal to in the limits of integration. You don't have to write that as long as you understand which integral is which. In this formula, both types of notation mean the same thing. I could either write integral from x equal to 0 to x equal to 2, or I could just write integral from 0 to 2. The way to understand this type of double integral is that the inner integral is paired with the dy, and the outer integral is paired with the dx. As long as we understand that, we don't need to write x equal to or y equal to on the limits of integration. Now, previously we did integral from 0 to 2, integral from 0 to 1, 4 minus x minus y, dy dx is equal to 5. But we don't have to do it this order. We don't have to integrate with respect to y first and then x second. If we wanted to, we could swap the dx and the dy. And then, of course, we would need to swap the orange integral sign with the green integral sign. What we could do is we could calculate the integral from 0 to 1, integral from 0 to 2, 4 minus x minus y, dx, dy. And I leave this calculation for you to check. This is also equal to 5. When we do these double integrals, there's nothing particularly scary here, I don't think. We're just doing an integral, and then we're doing another integral. And just remember that when we do the first integral, here is the orange integral. Because we're integrating with respect to x, we're going to pretend that y is a constant. As long as you remember that, it's just the same as you know. It's just doing two integrals, one after the other. Now, these two integrals were equal. When is that true? That's true as long as we have a continuous function. Fubini's theorem says if a function f is continuous on the rectangle R, and I've given two ways to write this rectangle here. It's either the set of all points x, y, where x is between a and b and y is between c and d, or there's a shorter, neater way to describe this rectangle. That's the closed interval from a to b cross the closed interval from c to d. The first interval is the interval of x, and the second interval is the interval of y. Fubini's theorem says that as long as f is continuous on this rectangle, then the integral dy dx is always equal to the integral dx dy. And this is what we're going to be using. For example, calculate the double integral of the function f over the region R, where f is the function 100 minus 6x squared y, and R is the region where x is between 0 and 2, y is between -1 and 1. In other words, we're asked to calculate the volume of the solid which is shown in this picture. So the first thing to do is decide, do we want to integrate dx dy, or do we want to integrate dy dx? In this example, the book is doing both of them. First, let's integrate dx dy. Now remember, the inner ones are paired together. The inner is x, so for the right-hand integral, we write 0 and 2. And the outer ones are paired together. dy is on the outside, so on the outside integral, that's the left integral, we write -1 and 1. Or we can integrate dy dx. If we're swapping dy and dx around, then we need to swap the integrals around. This is the same as the integral from 0 to 2, integral from -1 to 1, function dy dx. And I leave this for you to check. When you do your revision, when you rewatch this lecture or you read the book, check that you're happy with both of these calculations. Let's move on. Another example from the textbook. Find the volume of the region bounded above by z is equal to 10 plus x squared plus 3y squared, and below by the rectangle, x is between 0 and 1, y is between 0 and 2. We can choose whether we do dy dx or dx dy. In this case, for this one, the book is choosing to do dy dx. Y is between 0 and 2. X is between 0 and 1. And that's all I want to say here. You can check that when we do this calculation, you get 86 over 3. So that was double integrals over rectangles. Let's make this a little bit more difficult. Let's now talk about double integrals over general regions. Now, instead of integrating over a rectangle, we're going to integrate over just some region. In this picture, our region is the blue egg-shaped region. Again, we use horizontal lines and vertical lines to split this up into rectangles. And we're only interested in the rectangles which are completely inside R. Some of these rectangles are partly inside R and partly outside R. For example, this one, which I'm coloring in red, partly this is inside R and partly it's outside R. We don't want that. We only want the rectangles which are completely inside R. And then we do what we did before. We draw a cuboid on top of each rectangle. We add together the volumes of all the cuboids, and then we take the limit as the number of the cuboids increases to infinity, or the limit as the norm of the partition tends to 0. And that gives us our integral. So in practice, how are we going to do this? We're going to be using Fubini's film. Here's a slightly more advanced version of Fubini's film. Let's suppose everything is continuous. F is continuous, G1 is continuous, G2 is continuous, H1 is continuous, and H2 is continuous. Let's suppose we have a region like this. We have a region where we can describe the region by saying X is between two numbers, A and B, but Y we describe as being between two functions, between G1 and G2. Then our double integral of f over R is the integral where x is between A and B, and then integral where y is between G1 of x and G2 of x, f of xy, dy dx. Now note here on the left integral, or to think of it another way, the outside integral, we can only have numbers in our limits of integration. But for the inside integral, we're allowed to have functions. That's if we do the integral dy dx. We could do it the other way around. We could also integrate dx dy. Now look at the right picture at the top. Let's suppose that we can describe our region by saying y is between two numbers, c and d, x is between two functions, the function h1 and the function h2. Then the double integral of f over the region R is the integral where y is between c and d, integral where x is between h1 and h2, f of xy dx dy. Again, on the outside integral, we can have only numbers in our limits of integration. On the inside integral, we're allowed to have functions if we want. Let's do an example. Find the volume of the prism shown in this picture, whose base is the triangle in the xy plane, bounded by the x-axis and the lines y is equal to x and x is equal to 1, and the top of the prism lies in the plane z is equal to 3 minus x minus y. So we're going to be integrating the function 3 minus x minus y over the region, the triangle in the xy plane, over this triangle. Here's the triangle. Finding antiderivatives of the function is going to be easy, and getting the numbers is easy. But the key idea here is, what are the limits of integration? So that's what we're going to talk about. First of all, do we want to do dy dx or do we want to do dx dy? Let's do dy dx. And then let's look at the outside letter. Let's look at x. In the triangle at the top, what are the smallest and biggest possible values of x? In this triangle, the smallest possible value of x is 0, and the biggest possible value of x is 1. So our outside limits of integration are going to be 0 and 1. Now that we've done that, we need to move on to the inside variables. Let's talk about y now. Choose any value of x and draw a vertical line in your region. Here it is shown in red. On this line, at least just the part of this line which is inside the region R, what are the smallest and biggest possible values of y? The smallest possible y is right down the bottom. Here it is, I'm pointing with the green arrow. The smallest possible value of y is 0. And the biggest possible value of y is going to be at the top. The biggest possible value of y is x. So for our inside integral, the limits of integration are going to be 0 and x. After you've found the limits of integration, this is an easy problem. I'll leave this for you to check that the answer is 1. Now let's do the same problem, but now let's do it with dx dy instead of dy dx. Again, our strategy is the same. We start by looking at the outside variable. Here now the outside variable is the y. What are the smallest and biggest possible values of y in this triangle? Smallest is 0. Where's the biggest? The biggest is up here. The biggest possible value of y is 1. So for our outside integral, the limits are going to be 0 and 1. Next, let's look at the inside integral. We're going to look at the dx. Choose a y anywhere between 0 and 1 and draw a horizontal line. And just looking at the part of the horizontal line which is included inside R, what are the biggest and smallest possible values of x? Here's the smallest one. The smallest possible value of x is y. And here's the biggest one. The biggest possible value of x in this triangle on this line is 1. So for our inside integral, the limits of integration are going to be y and 1. And then after you know that, this is an easy problem. Let's move on. Fubini's theorem says that as long as everything is continuous, function is continuous, the boundaries of the region are continuous, then the double integral of f dx dy is the same as the double integral of f dy dx. But sometimes one of these integrals is easier to calculate than the other one. For example, calculate the double integral of sine x over the region R, where region R is the same one we just did. It's the triangle in the xy plane, bounded by the x-axis, y equal to x and x equal to 1. Now, if we choose to do dy dx, then it's easy. All we're having to do is integrating the function sine x. Very easy. But if we do it the other way, if we do the integral with dx dy, then I need an antiderivative of sine x over x. And that's not easy. In fact, if we do the integral with dx dy, this is a hard calculation to do. Do the integral dy dx, and it's actually easy. Let's talk more about finding the limits of integration. Let's find the limits of integration over this region R. It's bounded by the circle, x squared plus y squared equal to 1, and the line x plus y is equal to 1. The first question we should ask ourselves is, do we want to do the integral with dx dy or dy dx? First, let's try doing it dy dx. The answer will be at the bottom. I'm going to fill in the information as we get there. Next, we're going to look at the outside integral, the outside variable. We're going to be looking at x. So question 2 is, what are the smallest and biggest possible values of x in the region R? Look at the picture. We can see that x can be between 0 and 1. So for our outside integral, the limits are going to be 0 and 1. Next, we move to the other variable. Next, we move to looking at y. So what we do is we choose any value of x between 0 and 1, and we draw the vertical line through x. And I'm only interested in the part of the vertical line which is inside the region R. Question 3. What are the smallest and biggest possible values of y on this line inside R? Well, the smallest one is going to be down here. This one is going to be on the line x plus y equal to 1. So the smallest possible value is going to be y is equal to 1 minus x. What about the biggest one? The biggest possible value of y on this line is going to be at the top of the line, when we're on x squared plus y squared is equal to 1. So the biggest possible value of y is going to be square root of 1 minus x squared. And then we have our integral. Look down the bottom now. We would be doing the integral from 0 to 1, integral from 1 minus x to square root of 1 minus x squared of some function f of xy dy dx. Let's do this again. Let's now do it with dx dy. So question 1, shall we do dx dy or dy dx? Let's do the integral with dx dy in. Always start with the outside variable, start with the y. What are the smallest and biggest possible values of y in R? This region R I've drawn is symmetrical in the x and y, so we're going to get the same answer as before, but that doesn't matter. We can see from the picture that y can be any number between 0 and 1. So we can fill that in our formula at the bottom. Next, we need to find the possible values of x. So let's draw a horizontal line somewhere and ask what are the smallest and biggest possible values of x on this line in R. Smallest possible value of x is 1 minus y. The biggest possible value of x on this line is square root of 1 minus y squared. We can fill these in, and looking at the bottom, we find that we have the integral from 0 to 1, integral from 1 minus y to square root of 1 minus y squared, some function f of xy dx dy. Sketch the region of integration for the integral from 0 to 2, integral from x squared to 2x, 4x plus 2 dy dx. Then write an equivalent integral with dx dy. So first, let's draw a picture of our region of integration. We have 4 things to think about. We have x equal to 0, x equal to 2, y is equal to x squared, and y is equal to 2x to talk about. First, x equal to 0. That's easy to draw. Next, x equal to 2. Here it is, just a vertical line through 2. Y is equal to x squared. There we are. And then finally, y is equal to 2x. Is this? Now we can see the region of integration must be this region. It's the region between y is equal to x squared and y is equal to 2x, where x is between 0 and 2. For the second part of this question, we were asked to write down the equivalent integral with dx dy instead of dy dx. So let's find the limits of integration. First, we'll start with the outside integral. So first, we're starting with y. Looking at the picture, what are the smallest and biggest possible values of y here? Y can be between 0 and 4. And then we move on to x. Draw a horizontal line somewhere. What are the smallest and biggest possible values of x on this green line inside the region R? Here's the smallest. Smallest is going to be when x is y over 2. And for the orange arrow, the biggest one is going to be when x is equal to root y. Fill these in. The answer is integral from 0 to 4, integral from y over 2 to the square root of y, 4x plus 2 dx dy. I'm going to very, very quickly talk about some properties of double integrals. These should all be intuitive for you. There's nothing mysterious here. Let's suppose f and g are continuous on the bounded region R. The constant multiple rule, if we have some constant c, we can take it outside the integral. The sum rule, integral of f plus g is the same as integral of f plus integral of g. If f is always a positive function, then the integral of f must always be positive. If f is always bigger than g, then integral of f must be bigger than the integral of g. If our region R can be split into two smaller subregions, R1 and R2, in other words, if R is the union of R1 and R2, and R1 and R2 are disjoint, they don't overlap, then the integral of f over R must be the same as the integral of f over R1 plus the integral of f over R2. Straightforward, right? Next example. Find the volume of the wedge-like solid which lies beneath the surface z is equal to 16 minus x squared minus y squared, and above the region R bounded by the curve y is equal to 2 root x, the line y is equal to 4x minus 2, and the x-axis. We need the limits of integration. Let's look at y first. From the picture on the right, picture labeled B, we can see that y must be between 0 and 2. Draw a horizontal line and look at the possible values of x. X must be between y squared over 4 and y plus 2 over 4. And then after you know that, we can answer the problem. Just look at the formula that I put in a red box. We have the integral from 0 to 2, integral from y squared over 4 to y plus 2 over 4, and then our function, 16 minus x squared minus y squared, dx dy. And that's the difficult part of the problem done. All of this, the bottom part is just the easy bit. So let's not bother talking about that in the lesson. You can check this in your textbook. You can rewatch the lesson and pause here if you want. check that you're happy here. There's nothing mysterious going on in the easy part of this calculation. Now I'm going to set some problems for you to do. Look at this region. Which one of these is correct? I can tell you that the correct answer was B. Now let's do another one. Which of these is correct? The correct answer was A. Which of these is correct? This time we have 8 answers and 8 people who didn't respond. I can show you that actually this was a trick question. C and D were both correct. A and B were incorrect. Let's talk about C first of all. C says that x is between 0 and 3. Yes. For y, we draw a vertical line. Y is between 0 and 2x. Now let's talk about D. Y is equal to 2x and x is 3, so this must be 6. We can see that y can be between 0 and 6. Draw a horizontal line. X on the left of this line is y over 2, and on the right hand side of this line is 3. So x is between y over 2 and 3. One more, this is the final one. Which of these is correct? So far, 4 people have voted for A. Can I just remind you that on the outside integral, that's the left integral, you're only allowed to have numbers. So A is definitely not correct. And yes, I think you've got it. The correct answer was D. And this is a good point to have an 11-minute break. We'll continue the lesson at 2 o'clock. Now let's continue. Our next topic is area by double integration. The area of a closed bounded region R is the double integral over R dA. So basically what we're going to be doing is we're going to be integrating the function 1. For example, find the area of the region R bounded by y equal to x and y equal to x squared in the quadrant. A picture of this region. We need to find the limits of integration. Let's do dy dx. So first we're going to look for the limits of x, and then we're going to look for the limits of y. X is going to be between 0 and 1. Draw a vertical line. Where does the vertical line enter the region? Where does it leave the region? It enters at y equals to x squared, and it exits at y equals to x. So y must be between x squared and x. And then this is going to be straightforward. An antiderivative of 1 with respect to y is just y. So we have y calculated at x and at x squared. And then we need to do the integral from 0 to 1 of x minus x squared dx. Again, not too difficult. We have x squared over 2 minus x cubed over 3 calculated at 1 and at 0. And this is equal to 1/6. Let's do another one. Find the area of the region bounded by there's a mistake here. It should be y is equal to x plus 2. And y is equal to x squared in the first quadrant. Again, I've drawn a picture at the top. So we could do this by doing dx dy. But if we did that, we'd have to split this up into two regions, the region R1 and the region R2. First, looking at the region R1, y must be between 0 and 1. X must be between minus root y and root y. And then let's look at region R2. Now y is going to be between 1 and 4. X is going to be between y minus 2 and root y. We would have to do two integrals. Let's try it a different way. Let's do the integral with dy dx instead. Now looking at the right-hand picture, I can see that x must be between minus 1 and 2. And then y, looking at the vertical red line or vertical pink line, at the bottom we have y is equal to x squared. At the top we have y is equal to x plus 2. So we have the integral from minus 1 to 2, integral from x squared to x plus 2, dy dx. And I'll leave it for you to check that when we calculate this, we get 9 over 2. Find the area of the region R, described by x is between minus 2 and 2, y is between minus 1 minus root 4 minus x squared, and 1 plus root 4 minus x squared. I'll show you a picture of this region. Here we are. We want to calculate the area of this region. So we're going to do an integral. We know the limits. We're told the limits of integration in the question. I'm actually going to break this up into 4 pieces. 4 multiplied by integral between 0 and 2, integral from 0 to 1 plus root 4 minus x squared dy dx. When you calculate this, you can check that you get 8 plus 4 pi. There's another way to answer this question. I could say that the area of the region is the area of a circle of radius 2 plus the area of a 4 by 2 rectangle. So 4 pi plus 8. The average value of a function f over a region R is defined to be 1 divided by the area of R multiplied by the double integral of f over R. So basically what we're doing is we're doing the integral of f divided by the integral of 1. For example, find the average value of x cos xy over the rectangle R, where x is between 0 and pi, y is between 0 and 1. That's the rectangle, closed interval from 0 to pi, cross closed interval from 0 to 1. So we're going to use the formula. The average value of f is 1 divided by the area of R, that's the area of rectangle, that's very easy, multiplied by the integral of f over this rectangle. That's 1 over pi, integral from 0 to pi, integral from 0 to 1, x cos xy dy dx. And I'm doing dy dx because it's going to be easy to integrate this with respect to y. There's only one y here, but there's 2 x's, so doing it this way is going to be easier. An antiderivative of x cos xy with respect to y is just sine xy. So we want to do the integral from 0 to pi of sine x. That's easy. We end up with our answer 2 divided by pi. And that's all I want to say about that topic. The final idea for today's lesson, getting ready for the ideas that we'll do in the next lesson, is polar coordinates. This is back in chapter 10. If I wanted to describe the position of a point P in two-dimensional space, the usual way is to use Cartesian coordinates to give x and y coordinates, but that's not the only way to describe the position of a point. We could also use r theta coordinates, polar coordinates. R is the distance from the point P to the origin, and theta is the angle between the x-axis and the ray from the origin to P. Now, when we measure this angle, we need a convention. And the convention is that if we're measuring an angle anti-clockwise, then we say we have a positive angle. If we measure an angle in the clockwise direction, then we say that we have a negative angle. We can think of polar coordinates like this. Let's suppose we have a ruler, and this is a special mathematical ruler which also has negative numbers on, -1, -2, etc. And let's suppose we put this ruler so that 0 is at the origin and the ruler is along the x-axis. And then keeping 0 at the origin, I want to rotate this ruler by an angle of 45 degrees. Then we can look along the ruler and we can mark the points with polar coordinates. For example, this is the point with polar coordinates of 1, 45 degrees. The distance from this point to the origin is 1, and the ruler is making an angle of 45 degrees. Likewise, we have the point 245 degrees, the point 345 degrees, and so on. Here is the point 3.445 degrees, and so on. Let's do another one. Put the ruler back to its original position on the x-axis. And then this time I want to rotate it clockwise. And again, I'm going to keep 0 at 0. I want to rotate clockwise by an angle of 30 degrees, or using our convention, I'm rotating by an angle of minus 30 degrees. Then again, we can look along the ruler and we can draw the points 1 minus 30 degrees, 2 minus 30 degrees, 3 minus 30 degrees, etc. Now, polar coordinates are not unique. Let's look at this point P. The distance of this point to the origin is 2, and if we rotate our ruler 30 degrees to lie on this blue line, we can see that the coordinates of this point are 30 degrees. But I don't have to rotate my ruler anti-clockwise. Let's suppose I instead rotated my ruler clockwise by an angle of 330 degrees. Then the ruler would be in the same place. So we can say that the polar coordinates of this point are 2 minus 330 degrees. The difference between these two angles is always going to be 360 degrees or some multiple of 360 degrees. There's another way that we can get two different polar coordinates for the same point. If I rotate my ruler 30 degrees, so it lies like this, the point P, we could say, has polar coordinates minus 2 30 degrees. Imagine we've got our ruler like this. 0 is 0, minus 1 is about here, and then minus 2 is on this dot. Or I could rotate my ruler 210 degrees, but then the number 2 on the ruler would lie on the point P. So the polar coordinates of the point would be 210 degrees. If we do it this way, where the first numbers that are minus 1 multiplied by each other, then the difference between the two angles is going to be 180 degrees, or 180 degrees plus some multiple of 360 degrees. So, for example, find all of the polar coordinates of the point 230 degrees. There's two possibilities for r. We can either have r is 2 or we can have r is minus 2. We're going to talk about these two separately. First, what do we get if we use r equal to 2? We could have 30 degrees, or as we talked about last time, we could have 30 degrees plus or minus 360 degrees, or plus or minus 720 degrees, or plus or minus 1008 degrees, and so on. If we use minus 2, then the angle is going to be 210 degrees. That's 180 degrees more than 30 degrees. Or if we go all of the way around again, we could have 210 degrees plus 360, or plus 720, or plus 1080, or minus 360, minus 720, minus 1080, etc., etc. We could write down the answer to this problem as 2 30 plus 360 m degrees, or minus 2 210 plus 360 m degrees, for some integers m and n. Draw the graph of r equal to a. A is a constant. R is the distance from the origin. If the distance from the origin is always the same number, then we're going to get a circle. We don't know if a is a positive number or a negative number, so we write that the radius of the circle is absolute value of A. Draw the graph theta equal to B. Think back to the idea of putting the ruler on the x-axis, rotate it by an angle of B, and then you want all of the points along the ruler. We want a straight line which passes through the origin. So now let me just remark, r equal to 1 and r equal to -1 are the same circle. They're both equations for the circle of radius 1 centered at the origin. Theta equal to 30 degrees, theta equal to 210 degrees, theta equal to -150 degrees are all equations for the same line. Draw the set of points whose polar coordinates satisfy the following two conditions. R is between 1 and 2. Theta is between 0 and 90 degrees. Okay, so what do we have? First, R equal to 1. What's that? That's a circle of radius 1. Next, we have R equal to 2. That's a circle of radius 2. I'm trying to draw this with my mouse, but I'm not doing well. We know that R must be between 1 and 2, so we must be between these two circles. Next, we have theta equal to 0. That's here. And we have theta equal to 90 degrees, which is here. We must have an angle between the green and the blue lines. So where are we? We must be this region just here. Now I'll show you a picture I drew with a computer. And this is the answer. Draw the set of points whose polar coordinates satisfy the following. R is between -3 and 2. Theta is equal to 45 degrees. Theta equal to 45 degrees first, we must be somewhere on this line, because this is the angle 45 degrees. Where is R equal to 2 on this line? That's about here. Where is R equal to -3? That's about here. We must be on the pink line between the two blue dots. So this is the answer. Draw the set of points whose polar coordinates satisfy the following. R is less than or equal to 0. Theta is equal to 60 degrees. Imagine rotating your ruler by an angle of 60 degrees and then drawing just the numbers from which are less than or equal to 0. We have this set. Draw the set of points whose polar coordinates satisfy the following. Theta is between 120 degrees and 150 degrees. Think about the line theta is 120 degrees, the line theta is 150 degrees. We need to be between these two lines. So the answer is this region of points. We can relate polar and Cartesian coordinates together using these formulae. From the picture, we just use trigonometry to see that x must be the same as r cos theta and y must be the same as r sin theta. So of course, x squared plus y squared is the same as r squared, and tan theta must be y over x. I'll put these four formulae at the top for the next few slides. Convert the polar coordinates r theta is equal to -390 degrees into Cartesian coordinates. That's straightforward. We're just going to use the first two equations. We know r and theta. We want to calculate x and y. So just put the numbers in, and we get x is 0, y is minus 3. Now let's go the other way. Find polar coordinates for the Cartesian coordinates x, y is equal to 5 minus 12. Finding the r is going to be easy because we know x squared plus y squared is r squared. So r is square root of 25 plus 144 or 13. Next, we need to find a theta. And of course, there's infinitely many theta. I missed something here, by the way. We could always choose to have a positive r or negative r. And I think having a positive r is easier. So I'm using r is plus 13. You could use r is minus 13 if you wanted to. Next, we need to find a theta, and this time I'm going to use the equation y is equal to r sine theta. Rearrange that. Theta must be inverse sine of minus 12 over 13, and if you have a calculator, you find minus 67.38 degrees approximately. Now, it's easy to make a mistake here. It's easy to get the wrong angle, to be on completely the wrong side of the picture. So let's just draw a picture to see, does our answer look correct? Here's the point with Cartesian coordinates, 5 minus 12. Does this angle look like minus 67.38? Yes. So probably we didn't make a mistake. Using the formulae at the top, we can also write lines or curves in either Cartesian as easier. I'm sorry, as easy either a Cartesian equation or as a polar equation. This is the line y equals to 2, but of course, because y is the same as r sine theta, the polar equation for this line is r sine theta is equal to 2. Let's move to the next one. This is the curve x, y is equal to 4, or y is equal to 4 divided by x if you wish. That's the same as r squared cos theta sine theta is equal to 4. Next one. This is the curve x squared minus y squared is equal to 1. This is a hyperbola. Using the equations at the top, we can see that this is the same as r squared cos squared theta minus r squared sine squared theta is equal to 1. So far, these equations have all been easier using Cartesian coordinates, but that's not always the case. This curve is x squared minus 3x squared minus 4x minus 1 is equal to 0. Or if we use polar coordinates, that's the same as r is equal to 1 plus 2r cos theta, which I leave for you to check. And the final one, this type of curve is called a cardioid. X to the power 4 plus y to the power 4 plus 2x squared y squared plus 2x cubed plus 2xy squared y squared is equal to 0. If we use Cartesian coordinates, this is a complicated equation, but if we use polar coordinates, this is just the same as r is equal to 1 minus cos theta. I'll leave it for you to check that. For example, find a polar equation for the circle x squared plus y minus 3 squared is equal to 9. Now, this time, I want to use the formula x squared plus y squared is equal to r squared. So I start by multiplying out the equation so that I can replace x squared plus y squared by r squared. Here we go. And then what are we left with? We're left with minus 6y or minus 6r sine theta. Either r is equal to 0 or r minus 6 sine theta is equal to 0, but actually the second one includes the first one. So the answer is, this circle is the circle r is equal to 6 sine theta. And then we're coming to the end of today's lesson. The next section in the textbook is called Graphing in Polar Coordinates. It's a very small section. It's only 3 pages long. I would like you to have a quick read of those pages before next week. We're not going to be testing you on it. You're not going to have any homework or exam questions on section 10.4, but I think it can help you to understand section 14.4, which is what we're going to be studying at the start of the next lesson. So sometime in the next 2 weeks, please fit in 5 or 10 minutes just to read. That's all you'll need. You'll only need 5 or 10 minutes just to have a look at section 10.4. There's no lecture next week. Next week, you'll be having your exams for other courses. So for 2 weeks, you can stop thinking about calculus. In 2 weeks' time, we will finish chapter 14. We will do double integrals in polar form. We will be combining the ideas from today. We've talked about double integrals today, and we've talked about polar coordinates today. We'll put those ideas together. And then we'll start talking about triple integrals. First, triple integrals in rectangular coordinates, and then in section 14.7, triple integrals in cylindrical and spherical coordinates. That's another way of saying 3-dimensional polar coordinates. Finally, in the next lesson, we'll do substitutions in multiple integrals. Are there any questions? Second midterm exam, I'll announce it nearer the time, but you should expect it to be every lecture between the 2 midterms. So let me have a quick look at the syllabus. I expect it to be lectures 7, 8, and 9. I will not be reading the exam. The exam was run by Professor Hassan Uzekers. I'll make an announcement about the second midterm nearer the time, but based on past years, the idea is we would ask questions about lectures 7 to 9. You'll still be expected to know the material in the first 6 lectures, but the actual questions will come from the textbook in the chapters that we talk about in lectures 7, 8, and 9.